Welcome to the Introduction to Combinatorics Part 2. In our last video, we covered rule of product and rule of sum. We covered permutations, permutations with repeated symbols, permutations of nonlinear arrangements, and combinations. In this video, we will cover binomial theorem and combinations with repetition, these two topics being subtopics of combinations. And then we will look at two examples, the first one to illustrate the use of dividers, and the second to illustrate the dangers of double counting. So first we will explore the binomial theorem. So the binomial theorem, if x and y are variables and n is a positive integer, then x plus y raised to the n is equal to c to the n choose 0, x to the 0, y to the n, plus n choose 1, x to the 1, y to the n minus 1, plus n choose 2, x squared, y to the n minus 2, and so on. One thing to notice right away is you see these two exponents, the 0 plus n, the 1, n minus 1, the exponents in the x and y always add up to n. So the squared plus the n minus 2 will add to n. Anyway, to see why this is true from our combinatorics background, we'll consider x plus y raised to the third, which expands out to x plus y times x plus y plus x plus y. In particular, let's consider the x squared y term. To figure out what the coefficient of this term is, essentially what we're going to look at is the fact that we have three terms to choose the y from. So we might multiply this x times this y. That would give us 1x squared y. Or we could choose these two x's, and then we'd have a y term from here. Or we could choose an x from here, a y here, and an x here. Again, that would give us an x squared. So there are three possible ways for us to choose two x's. So in other words, this will be C of, from the three possible terms, we're going to choose two of the terms to take our x from, and the remaining term we will take our y. So our C, 3 choose 2, will be our exponent for our x squared term, x squared y term. So we just finished the binomial theorem. Our next topic will be combinations with repetition. This next topic, combinations with repetition, also known as stars and bars, is really interesting, which I don't know if that's a warning or not. But anyway, the problem that we're going to use to motivate the conversation is 7 students stop at a fast food restaurant where each of them has one of the following: a burger, a hot dog, a taco, or a fish sandwich. How many different purchases are possible? So the important thing to realize about this problem is what is important is how many of each item is ordered. So there are 7 students, they each order one item, and what we want to know is how many burgers were ordered, how many hot dogs were ordered, how many tacos were ordered, and how many fish sandwiches were ordered. It's a fast food restaurant, so we really don't care who ordered what. We just care about what goes in the bag when we hand over the bag, how many of each item. So this problem is quite different from what we've seen before, because it's certainly not a permutation, because we don't care what order people in what order people gives us the order. We just want to know how many of each item to put in the bag. And it's a combination, but we don't know how many of anything there is. So this really interesting problem has an interesting solution. And the idea is to pretend like you're maybe a waitress at this fast food place, and you're writing out a ticket that you're going to hand to the cook so they can cook the order. And rather, what you and the cook have come up with is a sort of shorthand. So you decide, you take these orders on a pad of paper where you have the items, burger, hot dog, taco, and fish sandwich written. As someone orders them, someone might say they order a hot dog, you're going to put an asterisk in that category. The next person might order a taco, the next person a hot dog, another person orders a burger, fish sandwich. So this is 1, 2, 3, 4, 5, 6, maybe one more order, 7. So this is one order. Another possible order might be something like this, where no one orders a fish sandwich. Anyway, at some point, maybe your shorthand becomes more and more evolved till eventually you don't even write the categories anymore. You just say a slash will separate each category. So this order here would represent the 1 burger, the 2 hot dogs, the 2 tacos, and the fish sandwich. And notice that for the 4 categories of food, you only need 3 slashes to separate them. The next order might look something like this. This is a totally new order I'm making up here. 1, 2, 3, 4, 5, 6, 7. So this would represent, let's see, let me get the marker, 3 burgers, 1 hot dog, 1 taco, 1 fish sandwich. Let me do one more order. This is going to represent 1 burger, no hot dogs, 1 taco, and 5 fish sandwiches. But the point isn't really to train you how to work in a fast food restaurant, and I'm not sure anyone would really appreciate you taking the orders that way. But what this will help us do is figure out how many different purchases are possible, because essentially what ends up happening is every order is going to be a sequence of 7 stars. And remember, the 7 stars represent the 7 items ordered. And then there's going to be 3 bars that are used to separate 4 categories of food. So now the question becomes, how many arrangements can I make of 7 stars and 3 bars? That should have been important. But this problem, how many arrangements of 7 stars and 3 bars, we know how to do this because we did this when we did permutations. It's a lot like that ALL problem. So basically we have 10 total symbols, and we have 7 stars and 3 bars. So this is your final answer. That's how many possible different orders there are. Another way I like to think of combinations with repetition or stars and bars is I like to think of the stars and bars as categorizing otherwise identical objects. Essentially, you're categorizing these identical stars. In the last example, these stars represented orders, and the reason why they were considered identical objects is because each order didn't belong to anybody. They're just some person's order. And then you're then sorting these into these categories. So it could be like the fish, the burger, the hot dog, or the taco. Then essentially you're going to take each of these stars and drop them into one of these categories. Another example is how many ways can 10 dimes be distributed among 5 children? So we're assuming the dimes are identical, that you're really not trying to keep track of the dimes. So now the dimes, as I said, were the 10 stars are going to represent the 10 dimes. For all purposes, they're identical. And then we're going to divide them among 5 children. And in other words, we're going to categorize each dime as belonging to child 1, child 2, child 3, child 4, or child 5. So we're going to need 4 bars to divide the 5 children, the 5 categories. And again, we think of this as child 1. We're thinking of this as child 1, child 2, child 3, child 4, and child 5. They have their piggy banks out, and we're going to distribute these 10 dimes somehow into their piggy banks until all the dimes are given away to someone. But we know how to do this. Again, we have how many ways can we arrange the 10 stars and 4 bars? Well, there are 14 items altogether, and there are 10 of the star types and 4 of the bar types. So this is the number of ways that we can distribute the dimes. Last example of a stars and bars. How many possible integer solutions to x1 plus x2 plus x3 plus x4 plus x5 equals 10? And actually, I made this example look a lot like our last one. So what we can think about is our 10 stars are going to represent 10 units. And by units, I mean, we'll think of them almost as dimes. But now instead of distributing them to children, you're going to distribute them to the 5 integers. So there are 4 bars separating the 5 variables, the variable x1, x2, x3, x4, x5. Okay, so how many ways can we arrange these 10 stars, 4 bars? Well, that again is going to be 14 factorial, 14 total, divided by 10 stars and 4 bars. Again, there is an analogy. The 10 units could be like 10 pennies that you distribute among 5 variables or 5 children. So now we've gone over combinations with repetition. We did go over that quite quickly, but there's a lot to this, so make sure you take a look at some more of the examples. So our next topic will be use of dividers. So to illustrate use of dividers, we have an example problem. How many ways can I arrange 3 books on 2 shelves so that there is at least 1 book on each shelf? So what I can imagine is that this is a 2-step process. First, I want to arrange my 3 books. After that's happened, I'm going to place a divider. And what the divider does is it tells me where I'm going to divide. Basically, it represents the divide between the 2 shelves. So if I have book 1, book 2, and book 3, this super interesting arrangement, if I place the divider here, that means book 1 is on shelf 1, and book 2 and 3 is on the second shelf. So how many ways can I do this? Well, to arrange 3 books, I can do that 3 factorial ways. My second stage, I'm going to place a divider. So if I have 3 books and I want at least 1 book on each shelf, I only have 2 ways of placing the divider. So my answer is going to be 12. 12 arrangements. There's a second method of doing this problem that comes to mind. Like many other combinatorics problems, there's often more than one way to solve a problem, which is nice because then you have a way of checking your answer. And this method is use of cases. And actually, use of cases is probably just as important as use of dividers. So the first thing we can do, the first case we could do is we could choose 1 book for the top shelf. And then we'll have 2 books on the bottom. We're left with 2 on the bottom, but we'll arrange those 2 books on the bottom. The other case is We'll choose 2 books for the top shelf, and we'll arrange those 2 books. On the top shelf. And essentially, we're left with 1 book on the bottom, which we don't need to arrange. So, to start with, choose 1 book for the top. So out of 3 books, we have 1 choice. And then we need to arrange, we're left with, if you want, you could say from the leftover 2 books, we're going to choose 2 for the bottom shelf, and then we need to arrange those. Or, alternatively, the other case is, from the 3 books, we're going to choose 2 for the top, and then we're going to arrange those 2 books. And then from the leftover 1 book, we'll choose 1 to put on the bottom book, and we'll arrange those as well. So you can see our solution is going to be 3, let's see, from 3 choose 1, there's only one way to do this, plus 3 times 2 times 1 times 1. So again, we have 12 arrangements. So now we've looked at use of dividers, and also we've looked at use of cases. So our last topic will be the dangers of double counting. So our example problem for double counting is, how many ways can I choose a team of 3 people from a group of 2 girls and 3 boys if I want to be sure the team has at least 1 girl? There are a couple of ways that this can be done, but let's just take a quick note. Without constraints, there are 3 choose 5, that's 10 possible teams. So our first method, we can consider there are 10 possible teams, and if we want to be sure that there's at least 1 girl, we can subtract the 1 all-boy team, since there are 3 boys, which means there are 9 teams with at least 1 girl. The second way to do this is with using cases. And cases are a good way to avoid double counting. We can have the case that there's 1 girl on the team, or possibly there are 2 girls, and there's no possibility of 3 girls since there's only 2 girls total. So if there's 1 girl on the team, we're going to choose 1 girl, and we're going to choose 2 boys. Our second case is we choose 2 girls, and we choose 1 boy. So I have to shrink this to give myself a little more space. So choosing 1 girl, so there are 2 girls, choose 1, and choose 2 boys from 3 choose 2. Or, working on the second half, I'm going to choose 2 girls and choose 1 boy from the 3. So here I'm going to get 2 times 3 plus 1 times 3. Again, I have my 9 teams with 1 girl, at least 1 girl. So I'm always a little wary of showing this because I don't want to plant these wrong ideas. This is a wrong way. Basically, I'm going to illustrate double counting. So I don't want to plant bad ideas in your head, but at the same time, it comes up often enough that I'm going to show you what's wrong. So again, we're looking at a 3-person team with at least 1 girl, and we're going to choose from 2 girls and 3 boys. So again, a wrong approach might be something like this. First we choose one girl. And in this way, we think that we're going to guarantee we have at least one girl, which is true. And then after we've chosen the one girl, from the 4 remaining people, we're going to choose 2 more. Again, this is a wrong approach, but the idea you can kind of see is that you're going to ensure that there's a girl, and then you're going to fill out the rest of your team. So what's wrong with this? Let's do a little diagram. Let's start with choosing one girl. Let's name our girls Helena, Sabrina. So we've chosen one girl from the 2. Now from the 4 remaining, choose 2. 4 remaining, choose 2. 4, choose 2. That means there's going to be 6 possible pairs of people. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So let's say the first pair of people might be the boy Sam and the boy Bob. But maybe the second possibility is the boy Sam and the girl Sabrina. Okay, I'm not going to fill out the rest. I filled out enough of this part of the tree diagram. But let's see what happens down here with Sabrina. If we choose Sabrina first, it's possible that for the remaining 2 we choose Sam and Bob. Or it's possible we choose Sam and Helena. Now, I've drawn enough of this tree diagram. As I said, I didn't fill it all out, but I've drawn enough so you can see where the problem is. Here, if we follow this branch, we get Helena, Sam, and Sabrina, which is the same team. If we follow this branch, we get Sabrina, Sam, and Helena. So here we have the same teams. So when we count how many possible teams we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We already know we're in trouble because the maximum number of teams we could have was 10, right? If there were no restrictions without constraint, there are 5, choose 3, or 10 possible teams. And the reason why we have too many is because of this double counting. So one of the big hints, or one of the big no-nos, something that's going to give you a clue that you might be double counting, it's in this step over here. So I'm going to summarize it this way. You will double count if you select from a subset and then put those not selected back into the pool for consideration again. So in this example, we had selected from Helen and Sabrina. That was our subset. And then we did go ahead and select Helena. Once we selected Helena, though, we reconsidered Sabrina again. We put her back into the pool for consideration for selection again. So that was the mistake. Once you select here, you don't want to have Sabrina being reconsidered. Similarly, once you've selected Sabrina, you don't want Helena to be reconsidered because then you get this kind of crossing over. So now we're done with our double counting warning. So we've covered all the topics in combinatorics. So good luck with your studying. And thank you for listening.